So batteries, sounds pretty boring, no moving parts. Sits there and runs your notebook, right? Well, the fact is at HP we do a lot of research and testing and development into the battery pack because that's eventually what you depend on to run your notebook. So we start at the component level, we go to the pack level, and we go to the system level and how that battery pack works with the system. So for those of you who have no idea what a battery pack consists of, it's a bunch of these. These are typically stacked up in different configurations inside plastics to make a battery pack. This is a cell. This is a lithium-ion cell. This is a standard size that hundreds of millions a month are made in the industry, and they're used in everything from consumer electronics to EV to toys to everything else. But this is the most common form factor, so from a price perspective, it's what we're driving into most of the mainstream products. A battery consists of positive and negative electrodes with some separator material. Looks like this. You've got, this is what's inside one of those cans. The technical term is a jelly roll. And it's because you've got electrode material like this, positive electrode separator. It's rolled up, shoved in a can, has a top cover welded on, electrolyte sealed up, and voila, you have a cell. Over the years, this has morphed a little bit to become something more efficient use of the space. The result is you have different form factors, like this is something we call prismatic, same manufacturing style. It's a wound electrode design, shoved in a different can after it's flattened out. But if you stack a bunch of these in a battery pack, you can use the space a little bit better. You can make it thinner if you want as well. So we use that in like some of the EliteBook 12-inch kind of models, like this. So you've got a bunch of these stacked in here. Lately, this is the third form factor, and this is what everybody's talking about these days with Ultrabooks and iPads and that sort of thing. The industry refers to them as pouch batteries. Most folks call them polymer cells because the original cells used a polymerized electrolyte rather than a liquid electrolyte. So I'll refer to them as polymer cells because that's how everybody knows them right now. And these originally were developed for things like this in your handheld market where you want something slim. The downside is there's no can, so it's not protected. It has to be protected by the plastics of the device. The other downside is they swell.
Can you hold that up a second?
A can can't swell, all right? You've got a cylinder, it can't swell. There's no place for it to go. Prismatics can swell a little bit. Polymers can swell a lot if they're not treated well, and that's where a lot of the R&D comes in, is formulating electrolytes, formulating cathode materials that allow you to get good cycle life without swelling. And we learned from that, if you don't treat them well, they swell. You can Google company name, swelling batteries, you'll see all sorts of pictures all over the internet of batteries bulging out the bottom of notebooks. That's because when these came out, nobody realized how sensitive they were to long-term potential abuse issues.
What causes them to swell?
Gas.
And what's the
Simple.
Is it temperature? Or
Temperature is a factor, charge is a factor, just over the life, cycling is a factor. So we found ways to mitigate the risk of swelling over time. We still don't use a lot of these because they're very expensive. They're about 2x the price per watt hour as a cylindrical cell, so they're the high-end products. We actually ship more of these in our consumer premium than in commercial products because the demand from our commercial customers is not for slim and sexy as much as it is for being productive, right? Although you'll see this in Ultrabook, you got no choice. If you want to go under 18 millimeters, this is 18 millimeters by itself. And if you have a panel on top, you can't get there. So a lot more of this in the future. The lab next door is where I do all the cell testing, and we do two things with cells. So we qualify things at the component level as well as at the pack level, as well as at the system level. So at the component level, The cells, there's a couple of ways that they can fail catastrophically. And that includes overcharging, which is a key one. So you're putting in much more current than the cell wants to have, much more energy. Temperature is another, and we can protect against that to some degree, but we can't keep somebody from throwing it in a microwave. Even something like a low voltage condition is not healthy for lithium ion cells. You start getting chemical reactions with the electrode material, the copper and the nickel, and you get some degradation. So there's electronics to protect them. So the cell testing happens next door. It's a very noisy room. We do two kinds of testing. One is the overcharge testing, and we'll do it at different rates of current. We'll do it at high rates, low rates over a long period of time, basically putting in 2x the energy that that cell really wants and making certain that it'll fail safely. We know it's going to fail. It has to fail, but that it fails safely. This far one, if you tweak that mouse there on the corner, just to make the display pop back up. Sorry. As you go by, you'll see what that is it's a temperature profile of cells that we're in testing in the lab next door. I've got a hood that's vented because we do blow things up. We do fail cells catastrophically on occasion, and they don't make our AVL. But what we're looking for is repeatability of a thermal cutoff when we overcharge them.